Come back, section 4.4 of chapter 4, indefinite integrals and the net change theorem. Okay, what are indefinite integrals? In this section, we introduce a notation for antiderivatives, review the formulas for antiderivatives, and use them to evaluate definite integrals. We also reformulate fundamental theorem of calculus part 2 in a way that makes it easier to apply to science and engineering problems. All right, indefinite integrals. Both parts of the fundamental theorem establish connections between antiderivatives and definite integrals. If you remember, definite integrals are integrals where you have number here and number here. Okay, number here and variable here is okay, but that gives you a function. Part 1 of the fundamental theorem of calculus states that if f is continuous, then this particular function, the area so far function, is an antiderivative of f. Part 2 says that definite integral from a to b fx dx can be found by evaluating the difference of capital F at b and capital F at a, where capital F is the antiderivative, is an antiderivative of f. We need a convenient notation for antiderivatives that make them easy to work with. Okay, just as derivative has d by dx or prime as a notation, for integration or antiderivative, we have a notation, and that notation is simply s, long s, without the limits mentioning it. Okay, because the relation between antiderivatives and integrals is given by the fundamental theorem, the notation integral fx dx is traditionally used for an antiderivative of f and is called an indefinite integral. Indefinite because limits are not mentioned. All right. So, in integral of fx dx is capital Fx, means derivative of capital F is little f. In other words, integral and derivative are opposites. Okay, so integral of x squared dx is, notice, increase the power, divide by the new power plus a constant. Why? Why is antiderivative of x squared this? Take the derivative of this. Derivative of constant is 0, so it contributes nothing, whereas this, the 3 comes down, cancels the 3, and you are left with x squared. So we can regard an indefinite integral as representing an entire family of functions. One antiderivative for each value of the constant c. I hope you understand what it means to say family of function. If c were 5, you get one function. If c were 6, you get another function. C equals 10, yet another function. C equals negative 20, yet another function. So for varying values of c's, you would get different functions. That's why it's called family of functions. Okay, family of functions. Family, the word is a collective, like you say bunch of flowers, you see, or you say a school of fish, or you say a group of students. Family is a collective term for functions. All right. Now, you should distinguish carefully between definite and indefinite integrals. A definite integral, integral a to b fx dx, because when you evaluate, you are going to result in a number. Whereas an indefinite integral, integral fx dx, is a function. Actually, not just a function, it's a family of functions, because general antiderivatives give you plus c. Now, the connection between them is given by part 2 of the fundamental theorem of calculus. definite integral a to b fx dx is, well, you find an antiderivative, evaluate it at b minus evaluate it at a. That's what this symbol means. Find the antiderivative, evaluate it at the higher limit minus evaluate it at a lower limit. So instead of, let's go back to our previous slide, section 4.3. Instead of, writing capital FB minus capital FA, say that capital F is any antiderivative of F, you can simply look at that. Write it as integral fx dx BA. So you can avoid all of this by simply writing this. Okay. Now, the effectiveness of the fundamental theorem depends on having a supply of. So you can find this if you know the antiderivatives well, right? If you know all the formulae. So let's do a few things. Any formula can be verified. Well, integral of secant squared is tan x plus c. Secant squared x, tan x plus c. Why? Because derivative of tan x plus c is secant squared. Okay. So let's review our derivative and integral formulas. Well, if I have a number inside multiplying my function, I can get it out. That's okay. Derivative of x is 1. So derivative of kx is k being a number. So integral of k is kx plus c. Derivative of cosine is negative sine. So integral of sine is negative cosine plus c. Derivative of tan is secant squared. So integral of secant squared is tan x plus c. Derivative of secant is secant x tan x. So integral of secant x tan x is secant x plus c. If I have to take integral of a sum of two functions, it is integral of the first plus integral of the second. What is integral of x to the power n? Well, increase the power of x by 1 and divide by the new power. Don't forget plus c. All of this makes sense as long as n is not negative 1. What happens when n is negative 1? Denominator becomes 0 and that is undefined. So this formula is not valid for n negative 1. So you have to take away that case. Integral of cosine is sine. Why? Derivative of sine is cosine. So integral of cosine is sine. Derivative of cotan is negative secant squared. So integral of cosecant squared is negative cotan. Derivative of cosecant is negative cosecant cotan. Therefore, integral of cosecant cotan is negative cosecant plus c. The most general antiderivative on a given interval is obtained by adding a constant. Do not forget to add a constant when you are simply looking for indefinite integrals. Alright, when you are looking at indefinite integrals, do not forget to write c. Okay, so integral of 1 over x squared dx equals negative 1 over x plus c. Now this you have to understand with the understanding that it is valid on the interval 0 to infinity or on the interval negative infinity to 0. Why? Because 0 is not valid, right? 0 is not a valid input for either this function or this function. So you have to choose an interval on which this is valid. So if you choose this, that's fine. This is defined here. If you choose this, that's fine. It's defined here. But you cannot define this on all of real numbers, okay? So be careful. We adopt the convention that when a formula for a general indefinite integral is given, it is valid only on an interval, okay? Okay, So what happens in the previous case? We had two different intervals. So you have two different constants. That's the point. So if your function is not defined on all of real numbers, it's defined only partly on one interval or another and so on, for each interval, you're allowed a different constant. All right. Now, we'll come to this example in a minute in the next video. Until then.